Hello, everyone, and welcome to the second keynote of a Monster Scale Summit. I'm Avi Kivity. I'm the CTO and a co-founder of ScyllaDB, and I'm here to present the ScyllaDB status report for this year. I'll be going over what we achieved in the last year and our plans for the next year, and it's going to be interesting. So a little bit about me. I wrote the first line for Linux KVM and maintained it for many years afterwards. And similarly with C-Star, I started the project and continue to maintain it. C-Star is the I/O engine behind ScyllaDB. And ScyllaDB itself, I wrote the first line and continue to write code. So let's continue. Like I mentioned, we'll be talking about the advances we made in 2024 and our plans for 2025. And they'll be mixed with each other just to add to the confusion. We'll be talking about maintenance and operations, security, performance and footprint, which are really total cost of ownership, advances we made in reliability and scaling, and the last will be features. Although there is a lot of overlap between those categories. Let's start with maintenance and operations. So for those new to ScyllaDB or for those that are using ScyllaDB Cloud, maintenance and operations are not something that you encounter, but for the people that run ScyllaDB Cloud and people using ScyllaDB Enterprise, they are very important. So one change we made is we switched to native node tool instead of the Java-based node tool. So this might appear as a cosmetic change, you just change the implementation language, but it really is a quality of life improvement to have the tool immediately print out the status of the cluster instead of spending a couple of seconds to start and tear down the Java virtual machine. We added the maintenance socket, which allows CQL connections even if the rest of the cluster is down. So you can connect directly to the node. It bypasses authentication. Now that might seem like as a security backdoor, but it is secured via Linux authentication. So if the machines that that host the nodes are secure, then we can use Linux security to secure the maintenance socket. It's a Unix domain socket rather than TCP. And it's useful to recover a node if a disaster happens. And lastly, we added the task management. So a lot of the internal operations that a node is performing are exposed as tasks, not just a node, there are also cluster-wide tasks that are exposed via this tool, and you can get a list of tasks and monitor their progress, cancel tasks, wait for tasks to complete, and we've added many categories. In the example below, you can see node tool task listing compaction tasks, which are the most common type of tasks the cluster is doing. Next, we implemented the native backup and restore. So up to now, backup and restore were done with a tool called rclone. And the problem with that is that because the bandwidth between rclone and ScyllaDB was shared, then we had to throttle rclone to a low bandwidth to reserve the rest of the bandwidth to ScyllaDB. And that meant that backup was pretty slow. By having native backup, so ScyllaDB itself is driving S3, we can utilize the full bandwidth, and the C-Star scheduler is able to throttle down backup when ScyllaDB needs more bandwidth and throttle it up again when ScyllaDB needs less bandwidth. So sharing the bandwidth to get better performance. It also exercises our S3 driver, which we're using for other features, which we'll describe later. And it reduces the RPO, so you can get the restores completed faster. And in the graphic, which I stole from another presentation in the summit, you can see the improvements in backup and restore time. In addition, backup and restore are tablet aware, so they maintain the tablet boundaries, and tablets can be restored directly. They are rack aware, so that the data backed up to one rack is restored to the same rack, and we can avoid duplicating the streams. And the same is in load and stream, which is one of our ETL tools. And there is a presentation, like I mentioned, that covers this in more detail. So we improved the repair. Repair is a process in which inconsistencies between the replicas are healed. So one thing we improved is small table repair. You might think that small tables should be fast, but the point is that we had quite a bit of overhead, which meant that the speed of small table repair was not proportional to their size. The overhead dominated over the data, and a lot of administrative tables were slow to repair because of that, and that is now much faster. And the next two features are things that are in progress. So automatic repair scheduling lets the cluster schedule repair of the tablet that was repaired least recently. And this avoids a sort of whack-a-mole problem where, let's say, you're using the node tool repair and you're repairing a node, but while you're launching your repair command, a tablet is migrated away to a different node. And then you repair that other node, but while you do that, the tablet is migrated back to the original node, and so it avoids getting repaired. So automatic repair can keep track of where tablets are migrating and not allow them to escape from repair. And finally, planned for later is incremental repair, which improves the efficiency of repair and therefore allows repair to happen more frequently. And repairing more frequently means that the tombstones can be garbage collected more frequently, and this improves read performance. Next, let's talk about security. The features on this slide are not new. They were ported from Enterprise, but they are new for the free version. So first, encryption at rest, both for SS tables and commit log. We can use lightweight directory access protocol for authentication and authorization. Again, this is mostly an enterprise feature, and on the cloud, you usually do not need it. And we added the audit so that you can keep track of DDL and even DML statements and the changes they do to data. New features in security are transitional authentication. So this allows you to transition a cluster that you set up without security. You really shouldn't do that, but let's say you did. It allows you to transition the cluster without downtime to a cluster that does have security. And we implemented the role-based access control for Alternator, which is our implementation of the DynamoDB protocol. Performance and footprint, or total cost of ownership. So again, an enterprise feature that we ported to the free version. It's already in production on our cloud. So link time optimization and profile guided optimization, those are compiler technologies that allow the optimizer to optimize the whole program. And we added the training scripts that allow the optimizer to take into account how the paths that are used in practice rather than all possible error paths. And the improvement is fairly impressive. So it's 30% improvement for what is basically a longer build and compile cycle. And it translates to either having fewer nodes or smaller nodes, or you can do more work with the same nodes that you already have. So compression, we already have dictionary compression for remote procedure calls. For that's internode communication, and that is important because it reduces traffic that crosses availability zones, which is very expensive. It costs 2 cents per gigabytes, and when you have a high throughput database, the gigabytes flow like water. And we are working on adding dictionary compression for SS tables. And here the goal is to get a better compression ratio, which in turn allow you to reduce your storage cost and store more data on the same amount of storage. I can talk for a few minutes about dictionary compression. So the problem both with RPC and with SS table compression is that the blocks we are compressing are very small. So RPC chunks are small because we are sending small messages. They can be a few hundred bytes in size or even less, depending on your workload. And for SS tables, we have to compress in small chunks because read performance demands that we load those small chunks in order to access a small amount of data. And regular compression does not work well with small chunks. It likes to have a large corpus to compress. And what a dictionary does is we sample ahead of time the data, either RPC traffic or SS table data. And that data becomes the context for the compression. So compression can find redundancies not just between data within a chunk, but also redundancies within a chunk and the dictionary. So that can provide impressive compression and either directly reduce your cost or increase the amount of storage that's available to you. And on the same theme, currently with vNodes, we usually require that there be a 30% free space on the node so that we have a buffer to allow for launching a new node and for streaming to complete. But with tablets, tablets both stream much more quickly, and also they start to remove data from the origin node before streaming is complete. So it's incremental. And it can be very fast, up to 10 gigabytes per second on the very largest of instances. So something like i3n.metal on Amazon or similar instances on other providers. And another thing is that it's schema independent. So our previous streaming implementation could be slower or faster depending on your schema. And with tablets, it's completely independent, so we can rely on the bandwidth to be high. And below you have a table, again stolen from a different presentation, that shows a dramatic performance improvements. And using this new technology, we can launch instances just in time. So when we see that a node's storage is 90% or more full, we can launch a new instance at exactly that point in time, and the data will be migrated faster than it is being filled, and so the cluster will remain with enough spare disk capacity. And of course, when you no longer need the extra storage, you just decommission it. So we will see clusters that are more dynamic than they typically are today. Storage tiering is another way to reduce TCO. And the way it is done is you place some of the data, the hot data, on fast and expensive NVMe, and you place the cold data on inexpensive but slow S3 or similar object storage. And the cluster is responsible for migrating between the hot and cold tiers. And for the initial implementation, we will target time series workloads, where it is very easy to define what the hot part of the data and the cold part of the data is by using time windows. So we will say that the recent past is hot data and the far past is cold data, and we will migrate between the fast storage and slow storage. Next, let's talk about reliability and scaling, where a lot of our focus has been with things like Raft and consistent topology. So we're moving more and more system tables into Raft. And those are tables like authentication and service level and change data capture metadata. And people who operate large clusters may be reminded of the problems we had in the past, where if you didn't operate the cluster exactly correct, then you would have periods of reduced availability or reduced performance due to hot nodes. So although we had caching for all of those tables, it was not perfect. And now with the data on Raft, the data is simply replicated to every node, so nodes do not need to access other nodes. And if you want to see what happens if your caches are cold and you have a storm of connections, then each node will attempt to locate the cluster node that stores the authentication data. Usually there are more replicas, but I wanted to simplify the animation. And if you have enough nodes, they can overwhelm the node that serves the authentication, and you will have reduced performance. But that is gone now thanks to having full replication of this metadata. And if you already have a cluster that uses distributed tables, then you don't need to worry. It's migrated automatically after you upgrade the software version. Next, we added support for nodes that are coordinator only. In ScyllaDB, nodes have two roles. One of them is the role of a replica that serves data, and one is a role of a coordinator that talks to clients and collects data from replicas. And that is a fully symmetric architecture, which is very convenient because you don't have to maintain two different tiers. But in some cases, it's better to have a two-tier architecture where you have a coordinator tier and a replica tier. And this allows you to do this architecture. And another case where coordinator-only nodes are valuable is when you have two data centers, and since we're using Raft for our metadata, then you can end up in a situation where if you lose a whole data center, then you lose quorum. So let's imagine that in this case we have 6 nodes divided into 2 data centers. If we lose one data center, then the remaining 3 nodes do not form a quorum, since for 6 nodes you need at least 4 nodes to form a complete quorum. So the solution is to introduce a coordinator-only node that is outside both data centers, and it can be a really simple single vCPU node that only serves as an arbiter. And this way, if one data center is down, then the surviving data center can form a quorum. So there will be 4 surviving nodes, 3 forms a surviving data center, and 1 from the arbiter node. And this quorum can continue, it can keep the cluster alive, it keeps the cluster metadata management running. Next, we're adding support to non-voting nodes. So in a democracy, everyone has a vote, but in clusters, it's not always a good idea. When you have very large clusters, then collecting a quorum can take a long time. You have to wait for every node. And Raft supports the notion of non-voting nodes. And in this example, you can have 3 nodes in one data center, 3 nodes in another, and yet another, and the arbiter node like we had in the previous example. It also solves the problem of asymmetric data centers. So if all of the nodes were voting, then the middle data center that has the larger number of nodes would form a quorum all by itself, and therefore would be vulnerable to network partitioning. If it were partitioned from the internet, it would still think it has a quorum, but with non-voting nodes, it only has 3 voters, and therefore, if it is partitioned, then it's not able to form a quorum, and the remaining nodes are able to make progress. Next, we simplify the schema healing. So in the forgotten past of ScyllaDB, schema was managed in a distributed way and with eventual consistency. So different coordinators could make changes to the schema, and then those changes that were concurrently made were attempted to be sort of reconciled. And that was both a problematic path, because sometimes there was no correct way to heal the schema. And also it was slow and buggy. So with Raft, we linearized the history, but we still had the old code that merges the schema still remained, and it still caused problems with large schemas. So these are no longer correctness problems, but they are performance problems. And now we eliminated that legacy code, and managing large schemas is efficient. We did work on the materials view write path. There's still much work left to be done, but we're making progress. So materials view updates are asynchronous, which means that some of the work happens after the main work of writing to the best table is complete. And this means that the remaining work can form a backlog. And if that backlog grows without bounds, then you will start having memory and performance problems. So we improved the algorithms for throttling writes. And we also improved the corner case where you have a delete statement that deletes a large number of rows. Say you're deleting a large partition, it would cause performance problems, and now it performs much better. We did a lot of work around the described schema. So we made sure that every little thing in the schema can be round tripped. So the statements you input to create the schema are fully reflected in described schema. This is useful for backup and restore, and for generating scripts to recreate the schema, perhaps for your continuous integration pipeline. And among the changes are all of the role and grants, so it can recreate your authentication scheme, including even the hashed passwords, and the change data capture, which was missing. Previously, internally, we used IP addresses to refer to nodes. And this is problematic when IP addresses can be recycled. So Kubernetes is a good example, but it's not the only one. And the problem is that the IP address today it refers to one node, and tomorrow it refers to another. So you can get your wires crossed and cause no end of problems. But now all of the addressing is done using the host UUID, and the host UUID is unique to a node, of course, and it cannot be recycled. So there is no chance of a node getting a message that was intended for a different node. We did more work around dynamic memory management. So the Bloom filter is a data structure that is held in memory, and it allows optimization of the read path. So an SS table can be dropped from the read path if it fails the Bloom filter. But the problem is that the Bloom filter memory size can be unpredictable. So in some workloads with some schemas, the Bloom filter can be very large. That's especially when you have a large number of very small partitions. So we added code that monitors the amount of memory taken by Bloom filters. And when you have an especially high demand, we throw away those Bloom filters. We trade off some performance for it, but trading off performance is better than crashing. And when memory becomes available, perhaps because you fixed a condition with lots of tombstone, then the Bloom filters are reloaded. And we also rebuild the Bloom filter if we notice that it's sized incorrectly. We added more cases where we check SS table checksums. And this is mostly on when the SS tables are not compressed. So this shouldn't happen a lot in practice, but it's still better to have all the cases covered. And it makes sure that if your SSD is flipping bits from 0 to 1 or 1 to 0, then you're not getting bad data. You will get an error instead, and you have the chance to isolate the node and repair the errors. Let's talk about the CQL features. So the first two here are, I guess, minor features in the grand order of thing, but I like them, maybe because I wrote the code for them. So the first is a not in predicate, which complements the in predicate. And the second is the set intersection, which computes the intersection between two sets, not very surprising. The third one is more interesting and unique to ScyllaDB. So with workload prioritization, which Felipe has an interesting presentation on, you can use service levels to designate different workloads and allow different applications or different workloads to coexist on the same data. And the way it works is that it uses the role that you log in with to define which workload you're using. And here we provide an escape hatch from that, so that you can say that the specific statement is using a different service level. The main reason we added it is to allow drivers to perform the initial queries in which they load the schema, to allow those initial queries to reduce their impact on the database and the workload. But perhaps there will also be use for it at the application level. And last, we added the vector data type. And again, there will be a more complete presentation about vector search. So we already support the vector data type, but the indexing itself is a work in progress. Unlike practically everything in ScyllaDB, this is not thread per core and even not distributed per node. So instead, we offload to a dedicated search engine. Our research indicated that the traditional horizontal scaling is not a good idea here. And offloading to a dedicated search node means that you can configure it in a different way. You can give it more memory, and you can use a GPU if you're able to get your hands on one. And it fixes the scaling problems that you would have with thread per core or with large clusters. And of course, tablets. So tablets are our main focus for next year, for the previous year, and maybe the year before that as well. So the plan is to complete feature integration. Right now, tablets work in the simple case where you don't use any of the extended features, but when you do, the code is still incomplete. So materials views is very close to completion for the simple case where the replication factor is equal to the number of racks, which happens to be almost all of the time, especially on clouds where you have availability zones. We will also later solve the complex cases, but of course we will start with a simple and common one. We'll enable tablets for change data capture and lightweight transactions, and counters features which is rarely used, but the people who do use it love it. We will leverage the fast scaling we have to reduce TCO, so it means better monitoring of storage and adjusting the streaming bandwidth to make sure we don't get stuck at 100% storage, at which point the node is not able to continue serving. We'll improve our tablet load balancing algorithms. So right now we're balancing on storage, and we're trying to get a tables footprint on every node and every shard to better respond to changing patterns. But we plan to also measure CPU use and perhaps do more interesting things, but let's wait for that to happen. And lastly, we may not be able to reach it this year, but we do plan to do it, is to have in-place migration from vNodes. So we have a very large installed base that uses vNodes, and we are not going to require customers to do the migrations themselves, and instead provide in-place migrations on their existing clusters so that they can enjoy the fun of tablets, and we can wave goodbye to the old vNodes code. And last, we will introduce a strong consistency model. So eventual consistency works well for many use cases, and lightweight transactions do provide strong consistency at the cost of some performance. But we would like to introduce Raft-based strong consistency that should provide higher performance and great reliability, standing on the shoulders of all of the people who built Raft, both in the industry and at ScyllaDB. And there will be a presentation about that as well. And that's all for me. Hope you enjoyed. Thanks a lot.